generate pseudo-random numbers. This source lib/random.py. This module implements pseudo-random number generators for various distributions. For integers, there is a uniform selection from a range. For sequences, there is a uniform selection of a random element. A function to generate a random permutation of a list in place, and a function for random sampling without replacement. On the real line, there are functions to compute uniform, normal, Gaussian, long normal, log normal, negative exponential, gamma, and beta distributions. For generating distributions of angles, the von Mises distribution is available. Almost all module functions depend on the basic function random, which generates a random float uniformly in the half open range 0.0 point 0 less than equal to x less than 1.0. Python uses the Mersenne twister as the core generator. It produces 53-bit precision floats and has a period of 2 power 19937 minus 1. The underlying implementation in C is both fast and thread safe. The Mersenne twister is one of the most extensively tested random number generators in existence. However, being completely deterministic, it is not suitable for all purposes and is completely unsuitable for cryptographic purposes. The functions supplied by this module are actually bound methods of a hidden instance of the random.random class. You can instantiate your own instances of random to get generators that don't share state. Class random can also be subclassed if you want to use a different basic generator of your own devising. See the documentation on that class for more details. The random module also provides the system random class, which uses the system function os.urrandom to generate random numbers from sources provided by the operating system. Warning: the pseudo-random generators for this module should not be used for security purposes. For security or cryptographic uses, see the secrets module. See also M.Matsumoto and T.Nishimura Mersenne twister A 623 dimensionally equi-distributed uniform pseudo-random number generator ACM transactions on modeling and computer simulation volume 8 number 1 January pp 330 1998 complimentary multiply with carry recipe for a compatible alternative random number generator with a long period and comparatively simple update operations. Bookkeeping functions. Random.seed a is equal to none, version is equal to 2. Initialize the random number generator. If a is omitted or none, the current system time is used. If randomness sources are provided by the operating system, they are used instead of the system time. See the os.urandom function for details on availability. If a is an integer, it is used directly. With version 2, the default a string byte array object gets converted to an integer and all of its bits are used. With version 1 provided for reproducing random sequences from older versions of Python, the algorithm for str and bytes generates a narrower range of seeds. Random.getState return an object capturing the current internal state of the generator. This object can be passed to setState to restore the state. Random.setState state should have been obtained from a previous call to getState, and setState restores the internal state of the generator to what it was at the time getState was called. Functions for bytes. Random.randBytes and generate n random bytes. This method should not be used for generating security tokens. Use secrets.token bytes. Functions for integers. Random.range stop. Random.range start stop step. Return a randomly selected element from range start stop step. This is roughly equivalent to choice range start stop step, but supports arbitrarily large ranges and is optimized for common cases. The positional argument pattern matches the range function. Keyword arguments should not be used because they can be interpreted in unexpected ways. For example, range start is equal to 100 is interpreted as range 0 100 1. Random dot rand integer int ab return a random integer n such that a less than equal to n less than equal to b alias for range a b plus 1. Random dot get rand bits k return a non-negative Python integer with k random bits. This method is supplied with the Merchant Twister generator, and some other generators may also provide it as an optional part of the API. When available, get rand bits enables rand range to handle arbitrarily large ranges. Functions for sequences. Random dot choice sequence return a random element from the non-empty sequence. If sequence is empty, raises index error. Random dot choices population comma weights is equal to none comma star comma cumulative weights is equal to none comma k is equal to 1. Return a k-sized list of elements chosen from the population with replacement. If the population is empty, raises index error. If a weights sequence is specified, selections are made according to the relative weights. Alternatively, if a cumulative weight sequence is given, the selections are made according to the cumulative weights, perhaps computed using iter tools.accumulate. For example, the relative weights 10, 5, 35 are equivalent to the cumulative weights 10, 15, 45, 50. Internally, the relative weights are converted to cumulative weights before making selections, so supplying the cumulative weights saves work. If neither weights nor cumulative weights are specified, selections are made with equal probability. If a weight sequence is supplied, it must be the same length as the population sequence. It is a type error to specify both weights and cumulative weights. The weights or cumulative weights can use any numeric type that interoperates with the float values returned by random, that includes integers, floats, fractions, but excludes decimals. Weights are assumed to be non-negative and finite. A value error is raised if all weights are 0. For a given seed, the choices function with equal weighting typically produces a different sequence than repeated calls to choice. The algorithm used by choices uses floating point arithmetic for internal consistency and speed. The algorithm used by choice defaults to integer arithmetic with repeated selections to avoid small biases from round of error. Random.shuffle x. Shuffle the sequence x in place. To shuffle an immutable sequence and return a new shuffled list, use sample x k is equal to length of x instead. Note that even for a small length x, the total number of permutations of x can quickly grow larger than the period of most random number generators. This implies that most permutations of a long sequence can never be generated. For example, a sequence of length 2080 is the largest that can fit within the period of Merchant Twister random number generator. Random.sample population k star counts is equal to none. Return a k length list of unique elements chosen from the population sequence used for the random sampling without replacement. Return a new list containing elements from the population while leaving the original population unchanged. The resulting list is in selection order so that all sub-slices will also be valid random samples. This allows raffle winners the sample to be partitioned into grand prize and second place winners the sub-slices. Members of the population need to be hashable or unique. If the population contains repeats, then each occurrence is also a possible selection in the sample. Repeated elements can be specified one at a time or with the optional keyword only counts parameter. For example, sample red blue counts is equal to 4 5 k is equal to 5 is equivalent to sample red blue k is equal to 5. To choose a sample from a range of integers, use a range object as an argument. This is especially fast and space efficient for sampling from a larger population. Sample range 1 0 0 0 0 0 0 0 k is equal to 60. If the sample size is larger than the population size, a value error is raised. Discrete distribution. The following functions generate a discrete distribution. Random dot binomial variant n is equal to 1, p is equal to 0.5. Binomial distribution. Return the number of successes of n independent trials with the probability of success in each trial being p, mathematically equivalent to some random less than p for I in range n. The number of trials n should be a non-negative integer. The probability of success p should be between 0.0 less than equal to p less than equal to 1.0. The result is an integer in the range 0 less than equal to x less than equal to n. Real valued distributions. The following functions generate specific real valued distributions. Function parameters are named after the corresponding variables in the distributions equation. As used in common mathematical practice, most of these equations can be found in any statistics text. Random. Return the next random floating point number in the range 0.0 less than equal to x less than 1.0. Random.uniform AB. Return a random floating point number n such that a less than equal to n less than equal to b for a less than equal to b and b less than equal to n less than equal to a for b less than a. The endpoint value b may or may not be included in the range depending on floating point rounding in the equation a plus b minus a into random. Random.triangular low high mode. Return a random floating point number n such that low less than equal to n less than equal to high and with the specified mode between those bounds. The low and high bounds defaults to 0 and 1. The mode argument defaults to the midpoint between the bounds, giving a symmetric distribution. Random dot b, beta variate alpha beta distribution conditions on the parameters are alpha less than greater than 0, beta greater than 0. Return values range between 0 and 1. Random dot expo variate lambda is equal to 1.0. Exponential distribution lambda is 1.0 divided by the desired mean. It should be non-zero. The parameter would be called lambda, but that is a reversed word in Python. Return value range from 0 to positive infinity if lambda is positive and from negative infinity to 0 if lambda is negative. Random dot gamma variate alpha beta gamma distribution, not the gamma function. The shape and scale parameters alpha and beta must have positive values. Calling conventions vary and some sources define beta as the inverse of the scale. The probability distribution function is PDF x is equal to x power alpha minus 1 into math.ie exponential minus x divided by beta whole divided by math.gamma alpha into beta power alpha. Random.gauge mu is equal to 0.1, sigma is equal to 1.0. Normal distribution, also called the Gaussian distribution. Mu is the mean and sigma is the standard deviation. This is slightly faster than the normal variate function defined below. Multi-threading note. When two threads call this function simultaneously, it is possible that they will receive the same return value. This can be avoided in three ways. 1. Have each thread use a different instance of the random number generator. 2. Put locks around all calls. Use the slower but thread-safe normal variate function instead. Random dot log norm variate mu sigma log normal distribution. If you take the natural logarithm of this distribution, you will get a normal distribution with mean mu and standard deviation sigma. Mu can have any value and sigma must be greater than 0. Random dot normal variate mu is equal to 0.0, sigma is equal to 1.0. Normal distribution mu is the mean and sigma is the standard deviation. Random dot von Mises variate mu kappa. Mu is the mean angle expressed in radians between 0 and 2 pi, and kappa is the concentration parameter which must be greater than or equal to 0. If kappa is equal to 0, this distribution reduces to a uniform random angle over the range 0 2 pi. The Pareto variate alpha. Pareto distribution. Alpha is the shape parameter. Random or V-bull variate. Alpha beta. V-bull distribution. Alpha is the scale parameter and beta is the shape parameter. Alternative generator. Class random seed. Class that implements the default pseudo-random number generator used by the random module. Subclasses of random should override the following methods if they wish to make use of a different basic generator. Seed A is equal to none, version is equal to 2. Override this method in subclasses to customize the seed behavior of random instances. Get state. Override this method in subclasses to customize the get state behavior of the random instance. Set state. Override this method in subclasses to customize the set state behavior of random instances. Random. Override this method in subclasses to customize the random behavior of random instances. Optionally, a custom generator subclass can also supply the following method. Get rand bits k. Override this method in subclasses to customize get rand bits behavior of random instances. Class random.system random seed. Class that uses the os.urandom function for generating random numbers from sources provided by the operating system. Not available on all systems, does not rely on software state, and sequences are not reproducible. Accordingly, the seed method has no effect and is ignored. The get state, set state methods raise not implemented error if called. Notes on reproducibility. Sometimes it is useful to be able to reproduce the sequences given by a pseudo-random number generator. By reusing a seed value, the same sequence should be reproducible from run to run as long as multiple threads are not running. Most of the random modules algorithms and seeding functions are subject to change across Python versions, but two aspects are guaranteed not to change. If a new seeding method is added, then a backward compatible seeder will be offered. The generator's random method will continue to produce the same sequence when the compatible seeder is given the same seed. Examples: random random module. Example 1: print random. Import from random, import random. Random between 0 to 7. Uniform 2.5 10.0. Print uniform. Uniform dot random uniform 7 point this. Expo variant 1 divided by 5. Expo variant 10 point that. Random range 10. Rand integer. Rand integer 10 5. Rand range. Rand range 0 1 0 1 2 90. Choice win lose draw. Print choices. Import random choice. Choices lose. Deck S234 dot split. Shuffle deck. Print deck. Import random dot shuffle. S432. Sample 10 20 30 40 50 k is equal to 4. The sample without replacement. random sample. Never ended. 40, 20, 50, 30. Simulations. 6 example 2. From random import star. Choice is red, black, green. 18, 18, 2. K is equal to 6. Run. Red, red, red. Black, black, black. 6. Black, black, red. Deal 20 cards without replacement from deck. 6 roulette wheels spin. Wait sampling with replacement. Deal Deal 20 cards without replacement from a deck of 52 playing cards and determine the proportion of cards with a 10 value. 10, Jack, Queen or King. Deal sample 10s low cards. Count 1636. K 20. 1636. Deal count 10s by 20. Print deal count 10s by 20. 0.25. Estimate. Estimate the probability of getting 5 or more heads from 7 spins of a biased coin that settles on heads 60% of the time. Binomial. From random import import random dot import underscore random dot y. This is not binomial variant. Random dot random dot binomial. Print is diff trial some trial this. Okay. Example of statistical bootstrapping using resampling with replacement to estimate a confidence interval for the mean of a sample. Print. From statistics import f mean as mean. From random import choices. Data is equal to this. Means is equal to sorted means mean choices data. K is equal to length of data for I in range 100. Print this. Example 3. Run. The sample mean of 49.0 has a 90% confidence interval from 40.0 to 58.9. Example of resampling permutation test to determine the statistical significance of p-value of an observed difference between the effects of a drug versus placebo. uh, Example, let's just run. Example 4. From statistics, import f mean as mean. From random, import shuffle. Drug is equal to this, placebo is equal to this. Observed difference, mean of drug minus mean of placebo. N is equal to 10,000, count is equal to 0, combined is equal to drug plus placebo for I in range n. Shuffle combined, new difference, mean combined length of drug minus mean combined length of drug, count plus is equal to new difference greater than observed. Print fn. We will understand this later. Simulation of arrival times and service deliveries for a multi-server queue. Example 5. Heap queue, import heapify, heap replace. From random, import expo variate cost. From statistics, import mean quantiles. Average arrival interval, this average server time, this standard deviation service time, this number servers 3 waits arrival time servers is equal to 00 dot number server heapify servers for I in range 1 lakh arrival time. These are all the calculations mathematical. Mean weight 20.4, max weight 297.2, quartiles 2.4, 12.8. See also statistics. Okay, recipes. These recipes show how to efficiently make random selections from the combinatory iterators in the ITER tool. Diff random product R's repeat is equal to 1. Random selection from ITER tools dot product. This pools is equal to tuple pool for pool in R's into repeat. Return tuple map random dot choice pools. Okay. The default random returns multiplies of 2 raised to 53 in the range 0.0 less than equal to x less than 1.0. All such numbers are evenly spaced and are exactly representable as Python floats. However, many other representable floats in that interval are not possible selection. For example, this is not an integer multiple of this. The following recipe takes a different approach. All floats in the interval are possible selections. The mantissa comes from a uniform distribution of integers in the range 2 raised to 52 less than equal to mantissa less than 2 raised to 53. Exponent comes from a geometric distribution where exponents smaller than minus 53 occur half as often as the next larger exponent. From random, import this. From math, import LDEX, EXP class full random diff random. Mantissa is equal to this, or self dot get rand beats 52. Exponent is equal to minus 53, x is equal to y not x is equal to self dot get rand beats 32. Exponent plus equal to x dot beat length minus 32. All real valued distribution in the class will use the new method fr dot full random, fr dot random, fr dot exponent. The recipe is conceptually equivalent to an algorithm that chooses from all the multiples of 2 raised to minus 1074 in the range 0.0 less than equal to x less than equal to 1.0. All such numbers are evenly spaced, but most have to be rounded down to the nearest representable Python float. The value 2 raised to minus 1074 is the smallest positive unnormalized float and is equal to math.ulp00. Thank you.